round reflection model, or simply we can say two-ray model. So this point is transmitter, this one is receiver, and this is the two-ray model, and which is we are now going to show. This is like this. You are seeing the clear picture of this. From this to this is a separation distance between the transmitter and receiver, that is known as TR separation, and it is given by D. And direct line of sight, direct means the this single direct path between the base station, or means tower or antenna, and towards the mobile, that is the receiver, that is here, and which is propagate from the initial end point to the final end point. So the most in the mobile communication system, the maximum TR separation distance is the most only in a few tens of kilometers. The earth here we have assumed as a flat, the earth surface we have assumed as a flat surface. So the total received E field, this is given by E total received field, is the sum of line of sight field plus sum of the reflected field. So it is the line of sight field LOS and reflected field EG. So take this figure into your account consideration. This is the height of from the surface of the earth. This transmitter is written by h of t, and the height of the receiver from surface to the receiver point is hr. So it is total geometry, and this is the our free space field, or this is the free space field, and here E naught is the free space field in units of V by M. So the term is here we used E naught, it is the free space field, unit is volt per meter, and that is the reference distance from the D naught, and it is the reference distance from the D naught from the transmitter. It is considered from the transmitter, and obviously here we have write, and this D naught is less than the separation distance between the transmitter and receiver. This D reference point is less than, it is in between the this point. So the free space propagation propagating E field, then we have given by this E field is given by the E field is given by, that is E is equal to because it is the distance and it is the time t, and is equal to E of reference point field, reference received point to the separation distance, and cos omega c t minus T by C. D is always greater than D naught. D is always greater than D naught. Before we are going in details, we having this some assumptions. That assumptions is like this. The first is height of the antenna are larger than the wavelength of the propagating wave. So that is means height of the antenna, height of the receiver is greater than the wavelength. Second is assumption, height of the antenna are lesser than the TR separation, transmitter receiver separation distance, that is given by H of T. H of R is less than D. Third is reflected waves are considered as grassing incidence wave. Reflected waves are considered as grassing incidence waves. And there is some parameters or terms are used for the estimation. So these parameters are, first is parameter which used in our derivation, E field of both rays, that is line of sight waves and the reflected signal, is given by respectively LOS and EZ, and the path difference is delta, and third one is the phase difference, that is the theta theta, and the time delay is another term, tau d, and one more is term is used, that is the AX, it is the vector quantity, and E naught is the amplitude of the wave, and alpha is attenuation constant, omega is the frequency, beta is the phase constant, and there is Z, it is the direction of propagation in electric field disturbance and propagating from near field to far field, and it is the AX unit vector, that is the direction of E field variation. So the term which we have used to drive this equation in this chapter is like this. First, this is the general equation z of t and E naught E minus alpha z cos omega t and beta z and ax. This equation is used in the EMFT. So EMFT, here we have, this is the general equation for plane wave in free space is given by this equation. Let us say it is the first. I'll now rewrite this equation with our own variables, that is d and t. It is d naught E naught do naught d and the cos terms omega c t minus d by c. Look at both equation, and now we are going to calculating the E field, that is line of sight. Before we moved, first of all you see these terms. Okay, we have, this is the cos omega c t minus d by c. Consider this term after a certain modification, and we got as similar. You have analyzed what we do now. We have taken this term inside the bracket, and now it is become omega c d by c. Okay, now take the cos term omega ct minus and open this like 2 pi fc dc. Okay, right now again we have write omega ct minus, this is 2 pi d by lambda. Okay, so we write this equation is omega ct, and this is nothing but this term 2 pi by lambda we can write in the phase form. This is beta t, right? In place of z we write the d, t is as it is, and all the terms which are here to use, that is the omega t bz is similar that these terms. So it is the similar to plane wave equation. So similarly we can write line of sight E field equation with the plane waves in a free space equation in our variable also, and the reflected wave, which is right as the LOS. Just one more thing is, see again this two-ray model. The distance from here to transmitter to receiver, this is the ELOS E field signal, and it is the single prime, and from distance from here to reflect back, that is given by D double prime. So now come back here, this is d bar of t and E do not d double bar cos omega c t d bar by c, and the reflected signal EZ is d double prime, and here is one more constant is gamma d double bar cos omega ct, d double bar c. So this is equation is right on the base of this our variable equation. Now if when we have put d equal to 0, if we put the d equal to 0, then free space does not hold. For this reason do not is used, and hence we modified this free equation. If we put the d naught, then it is not as our free space equation. No, we have right here when d is equal to 0, then free space does not hold. For this reason do not is used, and hence we modified free space equation. So it is written as PR distance as received power, PR at reference distance, and to the distance of Fraunhofer region. So we moved to drive the path loss. यानी कि we are going to first we are calculate the path difference. So see this equation. This is the this is the envelope of the amplitude point, amplitude part, and this is the phase part. See, this is the phase part, and this is the envelope of amplitude part. So the question is, if we have this a unit vector ax, for the sake of simplicity we have eliminated this equation in our derivation. So the question is, what will be E field for the line of sight signal and what will the E field for the reflected signal? So this is the line of sight E field, and this is the reflected E field signal. So the distance between the transmitter and receiver, the line of sight which is having we have taken the d prime, and the reflective ray distance between the considered as the d double prime. So the equation is now converted into this form. For if consider an ideal receiver means no loss. So what we do now, just add up all this received signal. After the adding, so E field equation is given by E total, right, is equal to E line of sight plus reflected E field, taking the mod. So E field E total is written here d naught upon d double. We put all this constant in here, put this values is here and this values is here, then we write is getting this equation. This is the line of sight reflective signal, and here this the E naught d double prime cos omega c t d double bar c And we know that from the law of reflection in dielectrics, and the reflection coefficient is -1. We know that from the law of reflection in dielectric and the reflection coefficient is -1. So in place of write the gamma function, we have put here -1. So what we getting after putting the values of gamma, this is modified once again, and this is d naught cos omega c t d bar by c plus -1 ed do d double bar, and again it is cos omega c t double bar by c. So this first part represent line of sight signal, this part is represent reflected signal. So for calculating we are going for calculating the path difference, that is delta. Since the path difference taken by the two rays are different and then is traveled at a different distances, therefore it is important to calculate the path difference. To find the path difference between the two waves, we have using the method is called method of imaging. Methods of imaging. For methods of imaging, what we do now, we have taken this two-ray model. This is the two-ray model. We have taken what? We have taken the mirror image of this two path loss model. So we extend this transmitter as